So I was watching a video by a Professor Tong, his name is, and he was talking about how the standard model came to be and that sort of thing, and so we're just going to kind of review that a little bit. The standard model is the particles that make up atoms. If I can find, these are the basic particles. They're called quarks, which make up the protons and the neutrons, and the quarks are based on spin. There's up quarks, down quarks, charm quarks, strange quarks, top quarks, bottom quarks, and there's I think there's two up quarks and one down quark in a proton, and one up quark and two down quarks in a neutron. The electron seems to be a particle in of itself. The weight of these other particles, muons and tau particles, I'm not exactly familiar with these. I don't know if these particles were created by having two protons or two electrons being forced to annihilate each other in LHC, which is called the Large Hadron Collider. I'm just going to, there's my background. I just need to keep re-updating my music here because it's kind of neat. I was looking for a better, first I wanted to mention the electron has a certain weight. These particles have certain mass, and the mass, evidently, it's described by the amount of energy which was used to create them divided by the speed of light squared, which in this case is megavolts. Mega electron volts divided by c squared. Now, as you can see, the weight of the electron is 0.5, the weight of the muon is 105, and the weight of the tau particle is 1,776. And I don't know if these particles were created by the collision of electrons or protons, or exactly how those were created. There's another particle. There's these particles. There's photons, gluons, which have no mass. A gluon, according to this, has 8 colors. Looks like the Higgs boson has quite a lot of mass. That was the new particle that was discovered. It only exists like 10 to the minus 21 seconds. Here's the particle families. So these are all called fermions. And these are called boson particles, of which a photon is a part of, which seems to have no color, and gluons, which have a lot of color. Now, I'm primarily interested in photons, which are created by the exchange of energy of moving electrons to different parts of the shell of an atom, called excitation. And depending on how that occurs, for example, if you look at the sun, you'll see a spectrum line, and you will see certain lines that are absorbed and certain lines that are emitted. Those are excitation lines, and photons are created on those wavelengths in order to let you know exactly what atoms, what molecular structures are being excited. and depending on the wavelength, it will tell you what is happening with those excitation energies, etc. And they're in the form of what's called Fourier transforms, which is they're like waves on the ocean, and there's one peak in the middle, and then there's these side peaks, which is the amount of energy that's left over from the excitation. The various particles. Now let's go back over here again. So quarks make up the protons and the neutrons of an atom. The electrons revolve around the atom. I don't know about the muons and tau particles. I'm interested in these gluons because they have these different colors. I'm wondering exactly how they're created and if there's a relationship between dimensions. Mediators of interactions are called bosons. In other words, an interaction occurs between atoms and particles are given off as a result, like photons. There are also antiparticles. In other words, for all of these particles here that exist, these are the quarks up top. There are antiparticles. They're called S particles. So in other words, an anti-electron is a selectron, a smuon, a stau, a bottom quark, a strange quark, a S down quark, and so on. S gluon. I don't know if there's antibosons. Let's actually look that up. This one professor says that bosons cannot have antiparticles because this property is restricted to fermions. Again, which are the particles on the left side of that standard model. The W and W plus and W minus bosons only differ by charge, so it's easy to mistake to talk about that in a way as particle and antiparticle, but it's just a pair of different charges. That's saying that charges are not what make up the antiparticle nature. Because there are force carriers. That would tell me that bosons exist in both dimensions. That's my bird jabbering. Bosons operate under different laws and can be created singly. Thus, this is a crucial distinction and is in nature of being either matter particles, or force carriers. I wish this thing would keep repeating, but it doesn't. So let's continue down this line here. So you've got gluons, photons, W and Z particles, and the Higgs boson's kind of out in left field. Instead, h bar, also known as the reduced Planck's constant, is used. For reasons that are beyond the scope of this book, the spin quantum number s, which is just a number, and the spin angular momentum, which is a number within a unit, are not numerically the same. Instead, they are related by a non-obvious equation. The angular momentum, s, is related to the spin and a reduced Planck's constant. I question the validity of Planck's constant, which is a little bit out of the scope of what we're studying. Planck's constant is based on a black body, and black body is a temperature coefficient curve, and which is also a standard deviation curve, but not in the way that you would typically understand a standard deviation curve. It's skewed, meaning it's skewed logarithmically, and it's sort of a different topic of conversation. But here you can see Planck's constant and 2 pi, which is a circumference, or can also relate to degrees, which is 180 degrees. Pi is related to radians, which is also related to the number of degrees in a circle. Now the spin of 1, which is in the photon, these bosons, photons, gluons, which is the particles I'm interested in studying, are related to Planck's constant, the square root of 2 times the reduced Planck's constant, which is kind of odd. Finnegan's Wake. Huh? There's actually a song by that name. Hadron, that's where the Hadron Collider name came from. Electron, match with the electron, etc. Neutrinos have very little mass. The reason why we're just going over this is we're studying particle nature, just to get a background of what exactly is going on with these particles. Quarks are known for decay products. These are the binding forces, the spring-looking things. These are particle interactions, electromagnetic charge, alpha particle scattering, interaction mediated by photons, releases a heavy particle. Quarks bound together, interaction mediated by gluons. Quarks are within protons and neutrons, so gluons keep the quarks together within the proton and neutron, so that's more of a heavier type of a particle. Electrons interaction are the lighter particle. So electron changes within atoms create photons. I guess. I'll just go into that in a minute. Reverse beta decay. That's radioactive particles. This is an electron. I don't know what exactly is going on there. There's two interactions occurring, and the W minus is this is a weak force that allows these changes to happen. Maybe. Gravity is not included in the standard model. Gravity is actually a weak force. The bosons associated with each force are called gauge bosons. The photon for electromagnetism, gluons for the strong force, and W and Z bosons for the weak force. So electromagnetism is a force that we study. It's represented by fields, and I don't know how they get photons related to electromagnetism, because photons are generally associated with light, which is an electromagnetic property. Charge is a property of matter. Now it says here gluons and photons have no charge. The W and Z particles have plus, minus, and zero charge associated with them. Charge exists in discrete amounts. This is the charge on one electron is 1.6 times 10 to the minus 19 coulombs. Quarks carry fractions of the charge. That's your protons and neutrons. Photons interact with these particles. They're carriers of results of interactions with those particles. Charged particles interact by the exchange of photons. The carrier of the electromagnetic force. Whenever an electron repels another electron or an electron orbits a nucleus, a photon is responsible. Photons are massless, uncharged, and have an unlimited range, which generally means infinity. The mathematical model used to describe the interaction of charged particles through the exchange of photons is known as quantum electrodynamics. That's QED for short. That forms a basis of the existence of photons and how they are used to represent these exchange of energies at certain wavelengths so that you can tell exactly where these energies come from. If I were to just look that up real quick, we could say, let's see, here's a good picture. So here's a picture of spectrum absorption lines, and the sun has certain elements like iron, calcium, hydrogen, and so on. And each of these lines represents the amount of photons that are emitted on those lines to show these interactions that are taking place. These colors represent a wavelength or a frequency. Let's see what this picture is. There's a slightly better picture. You can see, like, you'd have a device that measures the amount of photons in that each one of these lines, in these interactions at a certain frequency, and it tells you how much energy is located in these lines, and that energy is used to determine the atomic structure of it's reverse calculated to tell you what what elements are being interacted with due to heat and other things, I guess you could say. That's basically what that is. Now, if you look at this picture, this is an example of the black body spectrum, believe it or not. If I go to another, I didn't really want to get into this conversation. God. Here's a picture here. Now, if you look at these two pictures, you notice how they're pretty much the same. So this black body is based on temperature. But there's a problem in that the black body curve fails in the ultraviolet region. I'll just have to go into this again. I don't know if that's black body radiation. It's called the ultraviolet catastrophe. Rayleigh Jeans catastrophe was the prediction, etc., etc. Also, black body at thermal equilibrium will emit radiation at all frequency, emitting more energy as the frequency increases. By calculating the total amount of radiated energy, it can be shown that a black body is likely to release an arbitrarily high amount of energy, etc., etc. But the equation used to describe the black body formula fails at higher frequencies because there's what's called a classical theory, which over on the right hand side here, the ultraviolet catastrophe is the error at short wavelengths in the Rayleigh Jeans law, depicted as classical theory in the graph for the energy emitted by an ideal black body. The error, much more pronounced for short wavelengths, is the difference between the black curve, as classically predicted, and the blue curve, the measured curve predicted by Planck's law. So they're talking about this image. This blue curve right here, that's the curve predicted by Planck's law. Remember, we were talking about Planck's constant. And it talks about Rayleigh Jeans law is approximation of spectral radiance of electromagnetic radiation as a function of wavelength from a black body at a given temperature, and is given by this formula. Now, here they compare this to Planck's law, and they made a correction, I believe. See, then in the limit of high temperatures, a long wave is determined, and the exponential becomes small, and the exponential is well approximated by Taylor polynomials, first order theorem. I'm not going to go into the math of all that, but that's this section up here. In 1900, Max Planck empirically obtained an expression for black body radiation expressed in terms of wavelength. I believe that would be this formula, where h is the Planck's constant, which is right in there, which you can hardly see. The Planck's law does not suffer from an ultraviolet catastrophe and agrees well with the experimental data, but its full significance, which ultimately led to quantum theory, was only appreciated several years later, etc., etc., etc. The results reduces the black body formula to thus, which is identical to the classically derived Rayleigh Jeans expression. These are, when you see U, parentheses, lambda comma T. T is a temperature, lambda is, might be a wavelength, I'm not 100% sure. But if you look at the curve, though that formula expresses this curve at various temperatures, however, where did I see that? I thought there was another curve here somewhere. Damn. That's this one. This is infrared. These are longer wavelengths. And I'm actually wanting to study infrared frequencies. In other words, well, I don't know where the limits are of certain pieces of equipment like detectors, LED used for detectors are limited to certain wavelengths, which can act as a filter, which is nice. But maybe I want something that can pick up the noise at a very low temperature, because at the lower temperatures there's less noise. If I don't know, there's what's called noise figure. I don't know what this curve is. Noise figure, and noise temperature. Here's, if you look at this here, you'll see that bandwidth, more bandwidth is going to give you more noise. Noise figure is 10 log times, I'm not sure if F is frequency in that formula. There's a formula here. Noise figure in dB is 10 times the log base 10 of 1 plus the temperature divided by 290. And that describes a curve. Noise figure and noise, here's a good example. The ambient noise temperature at the antenna is 50 degrees Kelvin, let's say, and the gain of the antenna is 50 dB. Here the waveguide has a temperature of 290, etc., etc. So they use these temperatures and gains as a figure of how to figure out the noise in that whole system. Operating temperature T0 is your that's 20 degrees Celsius. I think it's like room temperature. No, yeah, I think it is. Let's see. God, I don't want to get into all of this. We're delving into everything that we need to take into consideration when it comes to building this equipment. I've course, that's not going to help me. 18 degrees C is 64 degrees. 21 degrees C is 70. So it's about room temperatures. It's 68 degrees. If we look at this chart, which obviously I can't see very well. So T0 is a room temperature noise figure at such and such temperature. Then it gives you a formula. F0 is a noise factor. I don't know what all that is. I've never seen that before. Now, this effective noise input temperature, if you have a very high resistor, you're going to have a very high temperature. And here you've got a noise source, and there's better ways to analyze this by just, you have to use a comparator type system to look at this. What else have we got here? This is called signal to noise ratio. You have a certain signal level, you have a certain noise level. What you do is you increase the amount of input at the antenna a certain amount, and you monitor the audio level at the output for a 3 decibel increase in power, and that tells you the sensitivity of your system. So we get into all that good stuff. If you are able to cool things down to a lower temperature, you can decrease that noise considerably. And getting back to all this other stuff, so you can see noise figure goes up with temperature, noise temperature in degrees Kelvin. There's a nice little formula there, I guess. rcafe.com. So there's that little discrepancy about this curve. This curve is related to Planck's constant, and for most intents and purposes it works. If we can lower the temperature to a much lower temperature at the input of our design curves, we might be able to eliminate, let's look up this Planck's law describes the spectral density of electromagnetic radiation emitted by a black body, which is basically what we're studying. But what if the temperature goes down considerably? If we can lower the temperature of a black body unit, can we eliminate see, here's the energy, the average energy curve from Planck's constant right here. The Rayleigh average of energy equals K times T. K, I think it's Boltzmann's constant. Now, there's another. Maxwell-Boltzmann distribution, speed of particles. The average particle speed is slightly higher than the most probable speed because the distribution is not symmetrical. Largest number of particles travel at the speed. What exactly is the Boltzmann's constant? Let's see, Boltzmann's constant is related to temperature. This is one of the things that I wanted to get into, is I want to relate Boltzmann's constant and Planck's constant to temperature. Lambda, I don't know if that's the wavelength. (760 N to 10 torr) for benzene, 300 degrees Kelvin. What pressure is needed to ensure this molecule travels from source to detector without a collision? 1 atmosphere. So if we could create a vacuum, if that number is less, if that number goes down, and we could lower the temperature. I think lambda technically means wavelength. That's joules per Kelvin. Chemical reactions also involve temperature. Coulomb's law, energy. This Q are charges. R is the radius between the charges. F is the amount of force, which is in, I don't know exactly what that is. The question hasn't been answered yet. It's pretty simple. But however, let me look. Stefan-Boltzmann law. Atoms in motion. Temperature, energy, Boltzmann's constant. Boltzmann equation. We're getting a little bit off the beaten path, but now here's something related to gluons. Now, so here's an example of different energy levels based on whatever interactions taking place. Number of particles with energy E. Maxwell-Boltzmann distribution. Now see, this curve is very similar to the black body radiation curve. X-axis, energy of particles, number of particles with a given energy. Conversion of energy to work. Calculating Boltzmann's constant. Tech lab experiment. Extrinsic, intrinsic regions. Anode, cathode. This would be a diode. That's an inductor. R equals 50 ohms. That's a capacitor. Temperature, control, values, numbers. What's this page? Source publication. Transient simulation of a class RF NPN BJT amplifier. In other words, these are simulating a 50 amperes switch subcircuit in a basic small. Yeah. Well, anyway, there's a relationship there. I'm not going to get into E equals KT. See, this is the formula. HV. I think it's Planck's constant. The velocity divided by Boltzmann constant times t approaches infinity. Average oscillator energy, HV. Freeze out of high energy oscillators. Predicts that oscillators with photon constrained energies greater than KT get significantly frozen out of the blackbody mix, thus solving the ultraviolet catastrophe to which Rayleigh Jean's model gave birth. This freeze out may be explained for whatever reason. Quantum oscillators exist only in packets with energy, frequency, momentum, etc., etc., etc. Packets have to do with energy. When electrons are excited and go to different energy levels within the atoms, and they release photons in packets, and if you have enough packets of energy released, you're going to get a waveform. This is the whole premise about my own work, is to relate the waveforms, or to study the waveforms, not necessarily the particles that make them up. But in order to do that, you've got to understand particle physics. You have to have a little understanding of it, and temperature. Temperature is so important. If HV is much greater than KT, the single photon fraction dominates as the average energy per oscillator drops to 0. That means accelerating at high speed and having the temperature low, using a low temperature. We can do that by using what's called the piezoelectric, the thermo. It's a device, a thermoelectric cooler, that we're going to use to lower the temperature of the input stages of this noise that we're studying. Number of oscillators and it's going through the roof. Average, Planck average goes down. This is HD divided by, if the temperature is very small, well, I mean, these numbers are so small to begin with. These are just equations related to energy, temperature, radiance versus frequency for Planck's law. Let's look at that. frequency divided by frequency per hertz. Just look at temperature. The coldest temperature is minus 273 degrees. Temperatures on computer circuit chips, you know, they're around, well, they can be cooled. Like, I mean, chips can be cooled down to minus 40, which is not a lot, but the thermoelectric coolers can get those temperatures down to where we can do something. We don't need that much of a difference, you know. I mean, minus 20 degrees, that's really cold. Like, if you were to go to, let's see, minus 20, that's actually not very cold. It's non-linear, though. Minus 22 is pretty cold. So that's the idea about temperature, and there's formulas and that sort of thing. But anyway, trying to get back to where we were. I was just going into that aspect of how Planck's constant and how that stuff's related. So we're back into reading this, quantum electrodynamics and photons, and then we can put our lovely music back on. Get back to where we were. What time is it? 5:30. Quarks stick to other quarks because they possess a characteristic known as color charge. Quarks come in one of three colors: red, green, or blue. The color is only an analogy. The colors of quarks in the standard model combine like the colors of light in human vision. Gluons glue quarks together, but they also stick to themselves. One consequence of this is they can't reach out and do much beyond the nucleus. That's important to know as far as particles are concerned. So gluons are the carrier energy binding force between the quarks within a proton or a neutron, and the work that we are doing does not concern, well, it may concern atoms because there are atoms in the air. We breathe oxygen, carbon, and whether those gluons can relate to other dimensions versus photons. Gluons are a strong force there. So I'm thinking not. Without the strong force, every nucleus would blow itself to smithereens. So this strong force is it's keeping the nucleus together. It's not something that would be used in communications necessarily. Now we've got weak forces. When a neutron decays into a proton, a W minus boson is responsible. We're not worried about mathematical model describes the electroweak theory. This convention Mass and gravity. Massless bosons. Massless bosons. That's my bird coughing. Oh God. So basically what we're looking at is what's called particle physics right here, which we're understanding how photons come into play, that fermions are, there's a group of called fermions which, okay, these are electromagnetic. I see what they're doing here. Those are the strong forces that bind the quarks together for the protons and the neutrons. You've got the quarks, leptons, and then you've got fermions and bosons. There's these names that associate. Bosons are the energy carriers. Fundamental particles are either the building blocks of matter called fermions or the mediators of interactions called bosons. And the boson that we are interested in is photon. It's because it's the only thing that we can mess with electrons and we can mess with photons. Because electrons are used in electronic circuits as well as photons. The photon somehow is going to be the carrier that exists between dimensions, or possibly gluons, or possibly some of these other particles. I don't know. But gluons are a force that we're not going to be able to measure. I don't know yet. We could look that up. Neutrinos are particles that are given off probably in radioactive interactions and that sort of thing. Standard model Lagrangian summary discussion. But we've gone over all of that. So there are some questions that are not really answered by... Now, F is force, I think. It's a force between two charged particles, which in a sense would be electrons, are positive and negative. It's related to gravity, this gravitational force. These are forces. It's just talking kind of in layman's terms, sort of. Then we have the more music playing. I like to listen to my music. So it talks here about 5 mysteries the standard model can't explain. So we just discussed the standard model of building blocks, the fermions and the bosons. Now we're talking about building blocks. Why do neutrinos have mass? We're not concerned about neutrinos. three neutrinos oscillate, because neutrinos are not massless after all. What is dark matter? They say that we understand 5% of the nature of the universe. The other 95% and what the universe is made up of, we don't know. So the Large Hadron Collider, actually, it's not an atom smasher. It doesn't smash the atoms and find out what they're made of. What it does is it actually creates particles, and particles are created during this process. And those particles that are created are the amount of energy that's released is how they determined the gluon particles, I guess, hold things together and that sort of thing. The universe is constantly expanding. Is there a particle associated with the force of gravity? Now, the Standard Model was not designed to explain gravity. This fourth and weakest force of nature does not seem to have any impact on the subatomic interactions. Theoretical physicists think that a subatomic particle called a graviton might transmit gravity the same way particles, called photons, carry the electromagnetic force. So they're saying that a photon exists in a magnetic field. Before I go back to answering that question, I'm just going to go over this other stuff. What else we got here? So the basic premise for having an antiphoton may not be true. What if photon can exist in two places at once, but what if the interaction of the photon can measure across dimensions somehow, because photons travel at the speed of light, or not, or faster? Let's see what this person's got to say here.
This is one of the most important announcements in the past decades.
It confirms, essentially, most of what has been done in physics.
This year's prize
great.
is about something very small that makes all the difference.
I'm rather surprised this happened in my lifetime.
At CERN's foundation in 1954, the world of particle physics was a very different one. Scientists were trying to come to grips with the plethora of particles observed in nature. They lacked an overall framework to explain these basic constituents of matter and the forces that act upon them. This framework would later become known as the Standard Model.
You can see they're talking about spin particles.
By the end of the decade, CERN physicists were already providing insights into the weak interaction, a force without which the sun would not shine. The 1960s saw the birth of electroweak theory, which unifies the weak and electromagnetic forces. A vital part of this is a mechanism that accounts for the vastly different ranges of these forces, as well as for particle masses. These were beautiful concepts, but they needed experimental evidence to back them up. Particle physicists embarked on a global search for the carriers of the weak force, W and Z bosons, whose existence would prove the theorists right. A major breakthrough came in 1973 with a discovery at the PS. The Gargamel experiment identified weak neutral currents, telltale signs of the existence of Z bosons. This groundbreaking result brought the first evidence for electroweak theory. Our physicists were on the right track, but direct detection of weak bosons would take another decade. In 1976, CERN brought the SPS on stream.
Look at those old computers they're using. Oh my God.
Larger and more powerful than CERN's previous accelerators, the SPS would go on to collide protons with antiprotons. By 1983, SPS experiments had seen W and Z bosons. Their long-awaited discovery led to the Nobel Prize for CERN's Carla Rubbia and Simon van der Meer.
This discovery of the W and Z is not the end. It is the beginning.
The next step began when LEP, the 27-kilometer Large Electron-Positron Collider, was switched on in 1989. It was designed to study weak bosons in detail. The LEP collaborations soon had their first major result. By measuring the decays of Z bosons, they found that nature has 3 and only 3 families of matter particles. Everything we see in the universe is made of the lightest family. During its 11 years of operation, LEP placed electroweak theory on solid experimental ground. The standard model was almost complete, but what accounted for the mass of particles? There was one last missing piece of the puzzle to uncover: the physical manifestation of the Brout-Englert-Higgs mechanism, a particle called the Higgs boson. Its discovery was in sight. With the construction of the Large Hadron Collider, CERN would take its first steps into a new century of discovery.
Today is a special day.
On the 4th of July 2012, the CMS and Atlas collaborations announced the discovery of Higgs bosons.
These results are the outcome of the ingenuity, vision and painstaking work of our community, from accelerator to detector, instrumentation, computing,
cool. In 3 dimensions.
and physics.
We have observed a new boson with a mass of 125.3 plus or minus 0.6 GeV at 4.9 standard deviations.
It was the final evidence the world had been waiting for, hitting headlines around the world, winning the Nobel Prize for Peter Higgs and François Englert, and cementing CERN's pivotal role in the development of the Standard Model.
There's that Lagrangian formula.
The Higgs boson completes the Standard Model, but many questions about our universe remain unanswered. Mysteries that will captivate future generations of scientists and lead them to untold discoveries.
Oh, if that's the same formula that was in that, I got rid of that web page too, I think.
Nobel Prize for Peter Higgs and François Englert, and cementing CERN's pivotal role in the development of the Standard.
It looks like some of that formula. I remember this piece. This is Xi and Yi. Those are positional. This is classical quantum theory, because they're talking about the actual positions of the particles. This is they've got MV here, minus 1/4 FMV, and HC, I'm assuming, is an energy. I don't know if that's Planck's constant times the speed of light. Yeah, that other formula that I had. I wonder if it's this page. Yeah, it's not. Standard particle. There's a lot of stuff down here. There's the formula right there. The standard model Lagrangian. That's what they're showing. That's phi, I think, not x. It's slightly different, but anyway, we're talking about particles. We have to understand the relationship between the particles. So what I'm dealing with primarily is it's okay. So we asked this question: what a photon is. Magnetic field is made of photons. Please do not use photons in your answer. Instead, as a combination of magnetic field and electric field. So electric and magnetic fields are made of the same stuff, photons. The shape of the field changes when two charges are present are those given by adding up the classical vector fields. So yes, there is a particularly strong field between the charges, but far away the fields tend to cancel. They can't even answer these questions. Electromagnetic fields are considered to be quantum objects. While this may be true, we cannot study quantum objects. We are studying fields. Lagrangian density for the free EM field is thus. This upside down triangle thing is scalar. That's scalar math. Maxwell equations. The zero divergence of B and Faraday's law of first and second equations allow the introduction of vector and scalar potentials A and phi, respectively. They give the fields. This is just the equation for, that's a double derivative of the area versus the time. Momentum, simple harmonic oscillators, representing a virtual magnetic field, possibly, quantization of EM fields. This is all classical mechanics. This is all classical. That's all that is, classical mechanics. So I don't know what they're trying to because I think I have a best grasp of normal photons, visible light, but such photons have defined energies and wavelengths, and they don't travel in a closed loop like a magnetic field appears to. The magnetic photon appears to be different than the normal photon, and I would like to understand why, if that is possible. The photons that contribute to magnetic fields are no different than the ones that contribute to electrical fields. Now see, the particular pattern of which phases are present for a different number of photons determines what classical fields are present, like the magnetic field, I guess, or an electrical field. A radio wave is a combination of electrical and magnetic, and depending on how you make your antenna, you can either have a magnetic distribution or an electrical distribution. Verticals are usually electrical, and horizontal antennas are usually magnetic. Which is interesting. Now see this, here's a good picture here. See, this is a half-wave dipole, and it shows you the electrical wave pattern coming in, how the antenna picks up the electrical portion. There's your two different fields in a radio wave. Oops. This is transmitting electrical fields. This is a horizontal antenna, and it's putting out these fields horizontally. But you can see they're actually contained within each other once they go outwards. Electrical fields are blue and magnetic fields are red. Magnetic antennas. Well, that would be a coil. Magnetic versus electrical antenna. The small loop antenna is known as a magnetic loop since it behaves electrically as a coil. It couples to the magnetic field of the radio wave in the region near the antenna, in contrast to a monopole or dipole which couple the electric field of the wave. The large self-resonant loop antenna has a circumference close to one wavelength of the operating frequency, and so is resonant at that frequency. You can make a smaller loop, adding a capacitor to make them resonant. In contrast, small loop antennas less than 1% of a wavelength in size are very inefficient radiators. A quad antenna is a resonant loop in a square shape. This one also includes a parasitic element. Polarization is important, depending on the feed line is connected. Small loops. Carefully designed and built small loops have advantages for reception on frequencies below 10 MHz. Although small loop losses can be high, The receiving signal-to-noise ratio may not suffer if the loop's diameter is at least 1 or 2 meters, regardless of the frequency. That's 3 to 6 feet in diameter. Very high Q rejects off-frequency interference. They usually consist of a single turn of large diameter conductor. % of the wavelength or less. Meaning, let's say if the wavelength of light is very small, so to capture the magnetic sections of light, that'd be a really small looking coil. Build two turns with series resistance less than half a wave, and an inductor for loops more than half a wave, less than a full wave. So a loop antenna, I mean, it's not practical to measure the magnetic portion of light. Even the weak signal and inefficient antenna are far above the internal thermal or Johnson noise present in radio receiver circuits. It talks about signal-to-noise ratio, magnetic versus electrical. Loop antennas are known as magnetic loop because it behaves electrically as a coil. It couples to the magnetic field of the radio wave in the region near the antenna. A typical noise chart. Thermal noise is minus 174 dBm per hertz. Noise at 7 megahertz is approximately minus 9 dB microvolts per meter in a 9 kilohertz. Atmospheric noise in the morning in the UK, that's all this stuff here. Frequency in megahertz. 20-30 dB of noise above thermal noise. Let's look up measuring the magnetic light. Measuring the magnetism of light. the standing light wave with magnetic generated in a photonic cavity as the light bounces between two reflection points that act like mirrors. The weaker effect of the magnetic component has been nearly impossible to detect directly. Now two groups have independently demonstrated that a tiny metallic probe will interact strongly with the magnetic field light waves trapped in any sort of semiconductor box. Nanoscale objects to map the magnetic field inside so-called metamaterials that can control light in new ways. Similar to how a laser is created, actually. If you use a metamaterial that has a higher response to magnetic fields, thanks to the sensitivity, light traveling through a metamaterial can bend in unusual ways, making feasible such devices as superlenses and invisibility cloaks. In the last few years, researchers have been characterizing the trapped light in photonic cavities by bringing the tip of a needle-shaped optical fiber within nanometers of the surface. This probe perturbs the electric field and shifts the trapped light into longer wavelengths. The new experiments use a fiber tip coated within a thin layer of aluminum that covers all but the very bottom of the tip. This aluminum of metal acts like a ring, a few hundred nanometers across. .03% within the cavity of their probe. Photonic crystal surface to construct an image using the spatial patterns of the magnetic field. The incoming and outgoing electric field of light shown as alternating red and white bands illustrates that the magnetic mirror retains light's original signature while a standard metallic mirror reverses it upon reflection. A magnetic mirror. Analysis through the looking glass to Wonderland, mirrors in the real world can sometimes behave in surprising and unexpected ways, including a new class of mirror that works like no other. It forgoes a familiar shiny metallic surface and instead reflects infrared light by using an unusual magnetic property of non-metallic metamaterial. By placing nanoscale antennas or very near the surface of these so-called magnetic mirrors, scientists are able to capture and harvest electromagnetic radiation in ways of tantalizing potential new class of chemical sensors, solar cells, lasers and other devices. Nanoscale resonators. They're using an element called tellurium, which is considerably smaller than the width of a human hair and even tinier than the wavelengths of infrared light, which is essential to achieve magnetic mirror behavior. Tellurium crystals. Conventional mirrors act by interacting with the light. Because of this, however, they do more than reverse the image. They also reverse the light's electrical field. Through this has an impact on the human eye. It does have implications in physics. Oh. So that's like changing the polarization. If I get rid of the electrical field, which is easy to do, then all that's left is the magnetic field. And how we do that, we would have one section of light going into, so like if I were to do, let's see, file, new. If I were to do, let's say, let's say, for example, we have two sources of light. Well, let's say we have, like, let's see, draw this. Let's say we have a source of light. Let's say that this light represents this here, okay? And we have if we have a mirror, here. This goes down to here. If I reflected it 3 times, well, I'm reflecting at 90 degrees. If I reflected at 45, if I put another device here, alright, so the first beam of light comes here, and it bounces off and goes here. Now, this is a reflected beam, so supposedly the electrical field has been reversed or taken out of phase. Oh God, I'm making things here. That's not what I wanted to do. me go back to our original color. I don't know why that dot keeps happening. So what we've got is we've got a wave here, and this wave here looks like this, and then we've got another wave here that's reversed, and it looks like this. And so what we've got here, and this is a detector. Okay, so we would write like let's see, white. So this would be this would be a mirror. And then over here, we have a detector. And so what we've got over here now, we'll go back to our colors, is in this detector, we have this. This. And theoretically, we've got a waveform that looks like this. Show up very well. Now, so in other words, these two waveforms will cancel each other out in the electrical field. So there's no magnetic change, but theoretically, according to what they're saying, is that if we combine these two fields together, then we should get zero electrical field, and we should get all magnetic. Now I don't know this. I don't know this for certain. So in this detector, we've got this output right here. We want to cancel an electrical field and then leave a magnetic field, which supposedly is, we can't measure it. But if we have like a coil or something, like a loop antenna or something, or if we have this tellurium, let's see if you can find anything on eBay these days. That's what I was looking for right here. If they made him into a heart. By one. I think you only get one of those cubes. The element is a semiconductor that shows a greater electrical conductivity in certain directions when exposed to light. It's used in making blasting caps. Lead telluride is used in far infrared detectors. Lead telluride, far infrared detector. It doesn't say what this shit's made of. I should know what material was in there. Optic technology. Is it the data sheet? I don't know. That's lead selenium. Germanium thermistors. Different from those germanium thermistors which are discussed in the paper. The crystal is cooled to temperatures low enough for the majority of dopants to freeze out. Drift motion of the carried. There must be a truck. Excellent applied electric field. Required to produce a single current signal current that's equal to the quadratic sum of all the noise currents in an electrical band within a change of frequency equal to 1 hertz. This is the ideal case. This is talking about particles. I don't think anything in here relates to anything. Wait, let's look at something else. Selector guide. Black body spectral radiant emittance. Oh, here's a good here's a good PDF. Optical materials, sodium chloride, quartz for infrared radiation, germanium, sapphire, This talks about infrared, which is heat radiation. Measuring. Yep. We'd want something that's pretty sensitive. I mean, it's metal package, cooling device, element thermistor, TE cooler, thermoelectrically cooled metal package. They even have those. That's a typical amplifier. TLO71. Now see, for what we're doing, where this input resistance is 1 megohm, that represents a lot of noise. That's your detector. It's not a good circuit. Electric materials. Something that's more responsive to temperature. One of those cubes is $8, but I don't know how they set this up. Conventional mirrors reflect light by interacting with the electrical component of the electromagnetic radiation. Because of this, however, they do more than reverse the image, they also reverse the light's electrical field. Though this has no impact on the human eye, it does have major implications in physics, etc. At the point of reflection, where the opposite incoming and outgoing electrical fields produce a cancelling effect. This temporary squelching of light's electrical properties prevents components like nanoscale antennas and quantum dots from interacting with light at the mirror surface. The magnetic mirror reflects the light by interacting its weak magnetic field, preserving its light's electrical properties. A magnetic mirror therefore produces a very strong electrical field at the mirror surface, enabling maximum absorption of the electromagnetic wave energy. Unlike silver and other metals, however, there is no natural material that reflects light magnetically. Magnetic fields can reflect and even bottle up charged particles like So tellurium is a dense material. First, the dielectric material they use, tellurium, which has a much lower signal loss than do metals, making the new design much more reflective at infrared wavelengths, creating a much stronger electrical field. The reflective properties of resonators emerge because they behave in some respects like artificial atoms, absorbing and re-emitting photons. Atoms naturally do this by absorbing photons with their outer electrons and then re-emitting them in random directions. This is how molecules in the atmosphere scatter light, etc. Metamaterials and resonators achieve a similar effect, but absorb and re-emit photons without reversing their electric fields. Okay. If efficient magnetic mirrors could be scaled to even shorter wavelengths, they could enable detectors, etc. In other words, I would use this, one of these blocks, as a reflector compared to a mirror. But it's actually creating, see, I've got front surface mirrors which are kind of like a metal, and they don't double refract. This would just reflect the light, but would keep the phase of the electrical. I don't know where the magnetic information comes into play there. I just don't know. It talks about that. It's not helping me. Does a photon include magnetic components? That's a good question. Photon doesn't have a, well, it has a spin of 1. And they represent 2 possible circular polarization states of the electromagnetic wave. So you could use polarizers. I've got some polarizers in my laser setup. 2 circular polarization would mean the field above rotating clockwise. Each photon is associated with X as its wave function, so it has a varying electric field at right angles to its velocity and a varying B magnetic field. A classical is caused by static electric give rise to static electric forces. B fields produced by moving charged particles, that is electric currents, gives rise to magnetic forces on other electric currents. So the fields are representative of a change in, but photons can't be constrained to the metal, to the coil. Photons have two possible spin states, +1 or -1. They correspond to the fields either clockwise or anti-clockwise, circularly polarized, where the E and B fields rotate with a certain constant angular velocity. Photons are associated with E and B fields. They carry no charge, so they are not affected by external E or B fields. They are, however, affected by charged particles. They can be emitted during energy changes, absorbed, scattered, reflected, refracted, diffracted, show interference patterns, pair productions, ionized certain materials. Wherever there's an electromagnetic field, the photon exists. It exists because there is a field. It is not the source of the field, however. To put simply, the particle-like interpretation of electromagnetic field involves photons which are particles constituting electromagnetic field. Okay. What is a magnetic field? The rules about conservation of magnetic field lines, for example, fall out of conservation of charge and momentum, but most people would rather just work with the illusionary magnetic field lines and then go back to basics every 5 minutes. Talking about, well, it doesn't explain a basic magnet, not an electromagnetic magnet, which is kind of interesting because I was kind of wondering about the magnet itself, or the magnet, exactly what are those particles coming out of a magnet, and how a magnet has a field. So if there's a field, does a magnet have an electrical field? Let's see. magnet, electrical field, similar to magnetic field, so it's two magnetic poles produced by charges, but moving charges, etc. They're saying yes. According to Faraday's law, you will get a current in a conductor when the amount of magnetic flux linked with the conductor changes. In other words, if you move the magnet, you can induce an electrical field. The flux has to change. Flux is the amount of the field. So how would I move? How would I move the? I would just change the electrical field within the magnetic field, and that's easily done by just impressing the light beam within a magnetic field somehow. And then so it's like you're getting back to this diagram. Let's say that we have this perfect mirror, and we have this detector that eliminates the electrical field, and then let's say we have a light wave that comes out of this, and that light wave, let's say this is a magnetic light wave that has a magnetic field, and any impressions that are made on it by entities from other dimensions are going to cause a change in that magnetic field. Let's say this is a changing magnetic field, and in order to, we could have a magnetic detector, a Hall effect device. We could use, so we could either have a Hall effect device, we could have a photodetector, we can't use a solar cell because the reactions are too slow, or we could have a coil. I think a combination of the different types of devices and the amplification necessary to get this light wave to if this is just the magnetic portion of the light wave, I mean, I think that's what we have to do. And the photons are going to be interacted with this idea of electrical and magnetic needs to be separated, because the electrical is going to add a lot of noise to the system. So if we have a magnetic amplifier, let's see, what if we write down, let's take a look at light lightweight magnetic amplifier. I got a bunch of these 12-volt transformers kicking around too. Well, the diodes convert to AC to DC, but magnetic amplifier. Homemade borax rectifiers. Magnetic audio amplifier. Phil knows what he's talking about. Yep. Now, this is another thing too, as far as resonant. If you can create a resonance circuit, like in this picture, going back to this picture right here, if we have, let's say we've got, no, that wouldn't work there, would it? I'm talking about resonance, like creating a resonance to amplify. I don't know. Resonant inductive coupling. And there's scalar antennas for coherent control of light. Electric energy density envelope. Polarization of light. Gas-filled waveguides, photoelectron energy. Second harmonic. PMT is a photo multiplier tube. Half wave plate. Lens sample. Lens analyzer. Reference quartz. Not sure what's going on there. That's water. They're reflecting light off of water to do something there. Second harmonic phase measurement. I don't know why the hell it just did that. So the idea that we're talking about is trying to get the magnetic information off of a light wave. You never know what you can find in here. Light wave optical pickup system. Disadvantages of electromagnetic energy. Well, I know I like the looks of that coil. It's an RF choke. Quantifying the magnetic nature of light. There's a Hall sensor there. Typical Hall switch. The infrared is in the nanometer. 700 nanometers. That's pretty big. Yes. Well, a thin dielectric film. Interference patterns. Yes, electrical and magnetic information would have interference patterns. This is somewhat technical. Air, mica, oil, substrate. I have quite a bit of mica as well, which I was going to use, but here they're actually using a spectrograph to look at the different aspects of light, which is kind of interesting. But this information in D has to be sent to an it has to be sent to a transducer to convert that energy into audio. That's sort of the whole idea. Sound transducer. It's like a piezoelectric microphone. They're saying the spirits don't use microphones. They use, it's all done with magnetic information. And that's kind of what we're dealing with. So, anyway, there's a discussion about quantum. The idea behind fields is what I wanted to get into, which I didn't really quite hit upon except for the magnetic lines of force. But light also has a magnetic characteristic, and whether or not white light's composed of many different colors, which has different frequencies. So that proves that light travels at different speeds. Light doesn't just have a constant speed because there's different colors. Is that my bird or is that me? Anyway, that's the topic of how we are going to relate this information and how we're going to build devices that convert the magnetic information to electrical. That's pretty much what we're trying to do. Oh, what's this here? These three photons bind together to make a molecule of light. Normally, photons do not interact with each other, and therefore will not bind together to form molecular-like structures. They're using ultra-cold gas of items and firing the laser beam into an ultra-cold gas, which I suppose is possible, but photon energy curved camera chips may be the next step in astronomical imaging. They use an optical cavity to control a propagating light pulse. They're talking about qubits, and they're talking about the optical cavity consists of two mirrors with a reflectivity of more than 99.99% facing each other, such that they can reflect a light pulse back and forth around 10,000 times. The light pulse thus interacts very strongly with the trapped atom. We trap a single rubidium atom in the resonator, which can then phase shift an impinging light pulse. If the atom is in equal superposition of the spin up and down states, the light pulse is brought into a superposition state as well. That's what it looks like, a cat state, a resonator. They've got this super cooled atom in here, and they got this light bouncing back and forth, creating this kind of a waveform, which is a resonant waveform, which is really what I don't want, because I want something that's active. But anyway, that's kind of the story behind quantum mechanics. And what we're going to do is we're going to get into talking about electrical and magnetic fields. In order to produce those, we have to have power supplies. We're going to build up some power supplies. I've got generators that we're going to study actual waveforms and create. We have to be able to measure very sensitive magnetic waves, and the Hall sensors can be found in broken up disk drives and stuff like that. So I gotta be looking for that stuff. I really don't feel like ordering a bunch of Hall sensors, although Let's see. I'm gonna sneeze. See, they're pretty cheap. I almost think I have some. I mean, look how cheap these are. I don't want to get it from Newark. Damn it. Those are $1 a piece. Oh, 10 pieces for $1? It says 10 pieces. These things are in old disk drives, and I got a bunch of them kicking around, but it's just 10 pieces. What does that mean? Do you get one for $1, or do you get 10 for $1? There's 20 pieces for $1.15. Does it get any better? I mean, really. Is that from the same company? These look different. These ones look different. They're from a different company. Why do they have those wires attached to them? Is there any reviews as product ratings? Two sold in the last 24 hours. Something to eat. Discontinued product. The device should not be purchased for new design applications. Samples are no longer available. See, it shows the position of the picture of the magnet here and the Hall sensor. This is an amplifier equals money. Hall effect. That's good stuff. Sensor in hard drives. HD clock hall sensor. HDD solenoid. Oh yeah, the DVD-ROM were in, well, it's just hard drives. Oh, I don't have mine.
Il me passe devant, hop. Ça me fait allumer une interruption. On va le faire marcher à fond. Je reset parce qu'il y a des parasites sur la ligne. Donc là la LED elle s'allume et elle s'éteint. On ne voit pas trop, mais si j'éteins le moteur, voilà. Donc là on le voit très bien. Et le signal que ça fait, c'est celui-là. Donc un superbe signal qui arrive.
I wonder what that was all about. So you can get they're in those drives. Oh god, this one's really messed up. You see that drive?
In a previous video I showed you this solenoid engine that we built from an old hard drive. In that video I told you that one of the problems with this motor is that the commutation is done mechanically by means of this wire that makes contact with the vertical axis and that introduces friction and wear. So in this video we will change that with the use of a Hall sensor switch. I have installed the Hall sensor and some other components, transistor and some resistors. I will show you the diagram later. We have two magnets on the rotor, this one and this other one. This magnet faces south and when it passes near the sensor, activates the sensor. Then the arm moves in this way and makes the rotor move. The other magnet faces north and deactivates the sensor, and the rotor continues by its inertia until the other magnet comes close and the cycle repeats. This keeps the disc spinning continuously.
You see, it's got to start it. That's cool. I like to watch some of this stuff. Well, he's got that baby going pretty fast there.
This is the diagram. Here we have the Hall sensor, a couple of resistors, PNP transistor, the power supply from 6 to 20 volts.
The Hall sensor inside of Hall sensor inside. My bird's talking. Just copy this.
Donc ici il y a
that there's something in there that measures. Maybe it's not a Hall sensor, it might be something else.
I thought I'd make a little video about what's inside of a hard drive. This is a 2.5-inch damage. Here's a solid state hard drive here in the center of this arm. So what we have is this disk is the platter. There's actually 2 disks on this drive. I don't know if the camera can pick that up, but there's 2 disks in this one, and they spin, and then the heads are on the tip of this little arm here, and this arm is motorized and can drive around and move the heads to different positions on the platters. And so the information is stored in circular rings or like a spiral around the disk, and that's where all the data is. On the cover, there's a rubber.
At any rate, I guess I'm done. I've kind of labored the idea about particles and that sort of thing. We're going to be working with fields. Again, I keep going back to this. Let's see. I have to make something to eat. So we have these fields around magnets. There's fields around light waves. We have to be able to detect these fields. And you can use coils, but that's not sensitive enough, I don't think. If we use the Hall effect sensor, picks up a signal that just acts as a switch. I don't know what the sensitivity of the switch is. It may not switch quick enough for audio. That would be easy enough to test, that's for sure. Doesn't say, does it? It's a switch. Uses a Smith trigger. Smith triggers. It works on rising and falling edges. Yeah, converts. It's probably better for analog to digital converter. There's another thing about the possibility of pulse width communication, or pulse width modulation. God, I don't know. That Hall effecting now, I don't know if I can use that for audio. I'd have to set up a calibration test for a Hall effect switch. $20 pieces for $1. High-speed linear Hall effect sensor. Linear Hall effect magnet sensor, or an amplifier in a package. A1346. God. Largest bandwidth 100 kilohertz. Linear Hall effect. I see. Yeah. It's probably not in there. Well, I don't know. I have no idea. But anyway, so we gotta do this. How are we gonna do this? Where are these damn sensors? speed, linear hold, achieving fast sent message response with what if that's on eBay? $8, 10 pieces. $503, huh? Hall effect sensors accurately track extremely small changes in magnetic flux density. This one doesn't have a Smith trigger. Flat response to 23 kilohertz, low noise output, 5-volt operation. To 10 hertz to 20. Broadband output noise. Well, wait, it said. What the heck did it say here? Flat response to 23 kilohertz. That's pretty good. $90 microvolts of noise. Shit, I lost that other spec sheet. Output noise is a function of frequency, so that looks good. Current to monitor. This one's discontinued. Discontinued. Doesn't say anything about the response. Magnetic flux density. Unlimited. Goes down to -40. I don't know. looks like the same type of circuit if you ask me. Maybe it's just an idea of testing a bunch of them out, you know? I'll have to look and see if I can find some somewhere. I don't know. I might even have some. God only knows, I got so much crap. But anyway, yep. So I am done. We're gonna get into just making power supplies. We're gonna get into calibration of magnetic equipment. I noticed nobody watched my stream since I've been on, which is like practical all night, but it will take time, I think, for people to sign up, and I have to set up some web pages probably, and God knows what else. So